In this lesson, we're going to look at implicit differentiation. So basically, this lesson will cover what implicit functions are, we'll look at the process behind implicit differentiation, and then we'll look at a bunch of examples. Now, basically, for our understanding, when we're looking at an implicit function or implicit equations, we're looking at a scenario where we have multiple variables and neither of them being isolated. So for a circle, an implicit form would be x squared plus y squared is equal to 1, or x squared plus y squared take 1 is equal to 0. So this is a circle with a radius of 1. The implicit form is that we've got neither of these variables isolated, where if we were to look at that in the explicit form, we could isolate y, and we would have y squared is equal to 1 take x squared, and y is equal to plus or minus the square root of 1 take x squared. So we've got two different forms of this same relation, the implicit form and the explicit form. Now, in terms of differentiation, it's actually easier to differentiate in the implicit form for a lot of different functions. And there's also a number of functions where there is no solution to a particular variable, and so therefore this process of implicit differentiation is important. So an example of that would be an equation where y could not be isolated. Could be something as simple as x squared y plus y squared x take 2y is equal to 3. So it's not possible here for us to be able to isolate that y, or isolating that y is beyond our current skill set. All right, so we'll move on now to that process of implicit differentiation. Now it is simply this: if we're trying to differentiate with respect to x, so d dx is differentiate with respect to x, then there's room for us to manipulate this, and we can say that d dx, if we split this d and dx, we can fill in with a third variable in between. And so if we're looking to try and differentiate with respect to y, but we're using d dx as an entire equation differentiation, we can fill in this extra variable dy. And so what that tells us is if we're going to differentiate with respect to y, we also need to multiply by dy dx. So it's a very simple manipulation, and this works in any case. We could have a d dn here, and we've got this third variable, which is t. So we could say this is d and dn and dt. So that's telling us if we differentiate with respect to t, then we'll need to multiply by dt dn. Now, of course, this only works for scenarios where there is a relationship between those two variables. So that being that we have an independent and a dependent variable in this case. All right, so a really simple example then, before we get started into the more complex ones, is we could just have y is equal to x squared. Now we know the derivative of this with respect to x will be dy dx is equal to 2x. If we take an implicit approach, even though this is an explicit function, we could say d dx of y equals x squared would be that we can find the derivative of y with respect to y, but we'd have to multiply by dy dx, so this would be 1 multiplied by dy dx, and derivative of x squared with respect to x, and that would just be 2x. So we end up with dy dx is equal to 2x in this case, which we know to be correct. So it's an implicit approach to an explicit function, just so you can see how it works. Now we'll look at some implicit functions with a couple of examples. Okay, so the first example, it's just saying for each of the following, find dy dx by implicit differentiation. So because we're looking at dy dx, we're looking at differentiating with respect to x. So for this first one, what we're saying is we're looking at d dx of x cubed is equal to y squared. Now this is the important part. We know that when we're differentiating this y squared with respect to x, we're going to have to multiply by dy dx. So pretty simple. The derivative of x cubed is 3x squared, and the derivative of y squared with respect to y is 2y, but because we differentiated with respect to y, we multiplied by dy dx. All right, the last step is we want to isolate dy dx to get our derivative, so divide by 2y, and we have dy dx is equal to 3x squared over 2y. Okay, so pretty straightforward. Part B, now we have xy is equal to 2x plus 1. So again, we're looking at d dx of this, and this is the issue here, this y. Now, we still have to follow our differentiation rule, so this one here is actually a product. So if we treat that as a product, we've got a u and a v, which is x and y. Derivative of x is 1, and derivative of y is 1 multiplied by dy dx. Because if we're differentiating with respect to x, we'll have to switch it over to differentiating by respect to y multiplied by dy dx. So it becomes 1 dy dx. And our product rule will be y times 1 plus x times 1 dy dx. So we've got y plus x dy dx. And so that means we end up with y plus x dy dx is equal to derivative of 2x is 2, derivative of 1 is 0. Now we want to isolate dy dx, so let's subtract y, and we have x dy dx is equal to 2, take y, divide by x, and we've got dy dx is equal to 2, take y on x. So nice and simple. Okay, so we can see that's pretty straightforward as long as we hold true to that understanding that if we differentiate it by that related variable, then we multiply by that rate of change. And then it's just a matter of isolating the rate of change. Okay, so example 2, we're looking to find the derivative dy dx if x squared plus y squared is equal to 1. Super simple, right? So because this is an implicit equation, we're looking to say d dx of x squared plus y squared is equal to 1. And we're applying this process of implicit differentiation. The first term is nice and simple. Derivative of x squared is 2x. The derivative of y squared is 2y, and we're multiplying by dy dx. Derivative of 1 is 0. So now we isolate. We have 2y dy dx, and we can subtract 2x from both sides. We divide by our 2y, so now we have dy dx is equal to negative 2x on 2y. And common factor of 2 cancels, and we're left with dy dx is equal to negative x on y. There we have our derivative in terms of x and y. Another example. Again, we're going to have this x and y, which is an issue, and this y. So if we say d dx of xy subtract x squared is equal to 0. This first one is a product. And so u is x, and v is y, u dash is 1, v dash is 1 dy dx. And we have y plus x dy dx. So that means we have y plus x dy dx, take 1 dy dx, so the derivative of y with respect to y is 1, multiplying by dy dx, take 2x, which is the derivative of x squared, and equal to 0. Now, if we keep all the dy dx's on one side, and we take the common factor, being dy dx, and we move everything over to the other side, we end up with dy dx, and we have x take 1 attached to the dy dx terms. And on the other side, we will have 2x take y. So we've added 2x to both sides and subtracted y from both sides. Dy dx will then be equal to 2x take y over x take 1 when we divide by this bracket. So we can't simplify this anymore. So here is our derivative in terms of x and y. Nice and straightforward. Okay, so in the next example, we're considering the curve with the equation 2x squared, take 2xy plus y squared is equal to 5. Part A, we want to find dy dx. So it's the same process, d dx of 2x squared, take 2xy plus y squared is equal to 5. We've got a product here, which means we're looking at u is equal to negative 2x and v is equal to y. Derivative of that is negative 2. Derivative of v is 1 dy dx. And so that outcome of the derivative will be negative 2y take 2x dy dx. And when we look at the derivative in its entirety, derivative of 2x squared is 4x. We will have negative 2y take 2x dy dx. And derivative of y squared is 2y dy dx. That's an implicit derivative. And derivative of 5 is equal to 0. So now all we need to do is isolate dy dx. Common factor with dy dx is 2y and negative 2x. And we can add 2y to both sides and subtract 4x to both sides and divide by the bracket 2y take 2x to isolate dy dx. So we have 2y subtract 4x over 2y subtract 2x. Common factor of 2 in the numerator and denominator, so we can now say dy dx is equal to y take 2x over y take x. Okay, so that's nice and simple. Part B says find the gradient of the tangent to the curve at the point 1, 3. So basically, they've told us that we want to find the gradient, we want to find dy dx when x is equal to 1 and y is equal to 3. So that's nice and easy to do. The gradient is equal to y take 2x, so we've got 3 take 2 times 1, over y take x, so we've got 3 take 1, which means we have 3 take 2, which is 1 over 2. So the gradient is 1/2, or the gradient of the tangent is 1/2 at the point 1, 3. Okay, so this is the last example, and we're taking a little bit of an extra step here. We're looking at the second derivative. So we'll step this out. We've already looked at this first derivative, but we'll do it again quickly. d dx of x squared plus y squared is equal to 1 will be 2x plus 2y dy dx is equal to 0. Subtract 2x, divide by 2y. So we have negative 2x on 2y, and our dy dx is equal to negative x on y. So that's nice and straightforward. Now, if we need to find the second derivative using an implicit process, this is what it is. So we're looking again to say d dx of dy dx and negative x on y. Now we can see on this side that's just going to give us our d squared y and dx squared, which represents our second derivative. And on this side, it's going to be a quotient. So this is a quotient rule. U is equal to negative x, v is equal to y. derivative is equal to -1, derivative is equal to 1 dy dx. And when we put that all together, the vu dash and uv dash, we'll subtract that over v squared. It looks like -y plus x dy dx all over v squared, which will give us our y squared. Now there's only one slight problem, and it's this. We've got this dy dx in there, and we need to be able to replace that. Now the good thing is we know what dy dx is equal to. We know that it's equal to -x on y, so we can replace that. So now we have -y plus x multiplied by -x on y over y squared. Now this just becomes a nice simple algebraic process. We want to get both of these terms on y so we can manipulate it. So this becomes -y squared on y, and we've got -x squared on y already. So multiply this one by y on top and bottom to get it to -y squared on y. Now this is all over y squared. So now we have -y squared take x squared all on y squared. And so that will simplify out nicely. This y will come down, and we have -y squared take x squared over y cubed. Or, so d squared y dx squared is equal to -x squared plus y squared all over y cubed. There it is. And that's how we find our second derivative when we're looking at an implicit process. All right. So that concludes the lesson. Hopefully this process makes sense. Practicing it should lead to fluency. In a lot of cases, it's a better approach than rearranging to isolate a variable and create an explicit function. Thank you.